Swayam Prabha. Digital India. Educated India.
Welcome. We are discussing the topics in the class high performance computing for scientists and engineers, and we are now discussing the second module of this course, OpenMP programming, and this is the this is a part of ongoing lectures on OpenMP programming, and today we will discuss about essentials of OpenMP programming. In last 3 classes we have discussed about some important features of OpenMP programming. I tried to introduce what is OpenMP to the students, and then we discussed how OpenMP works at system level and what are different type of memory handling in OpenMP, especially shared and private variables. And with this what we will discuss today is some, as the name suggests, the essentials of OpenMP programming, that some of the constructs and directives which are essential to write OpenMP program. And the idea is that you can start writing your own OpenMP program if you are aware about these particular constructs and directives and the associated clauses also. So let us look into it in detail. So we will discuss about OpenMP environment routines, directives and constructs. Some of the environment routines as well as some of the directives and constructs we have discussed in the last few classes, but we will formally see what are these and what are different classification of directives and constructs. We will look into that. Work sharing in OpenMP. While discussing work sharing, I will again touch upon this point that OpenMP is gives us a parallel paradigm which is portable, which is extremely portable. That means you can go to large supercomputers with say NUMA type of access, even multi-processor system, or you can look into your own desktop computer which has multiple processors and use same OpenMP program. And therefore, when you are using simple systems to do run your OpenMP program, it becomes also important that the resources are effectively used by OpenMP so that you get right parallel performance. And that is why how the parallel distribution will be done, how the mapping will be done, how the load balancing will be done, these are important. But fortunately, because OpenMP is also written for people who who are beginners in parallel program, they usually have their own scientific computing algorithm and they want to utilize parallel efficiency using different sorts of machine, and most of the time they are using their desktop or PC or a small workstation they are having. So for them, learning the details of load balancing and finding out which processors are free at which instant can be difficult. Also for this type of systems which are not dedicatedly developed for parallel computing, like your PC or like an workstation, these are not dedicatedly designed for parallel computing. Also these are not dedicatedly devoted for parallel computing, somebody else is probably also running some job there. So in order to understand which processors are relatively free and how the jobs will be distributed, that requires some different level of expertise, which is not always expected from a person who is working on OpenMP, because OpenMP is mostly for scientists and engineers and people from other domain who have some application and they want to get the parallel performance out of it. So while we look into work sharing, or while you look into the scheduling also, we'll see that the load balancing part is some way automatically taken care of by your OpenMP compiler, and we also have certain flexibility on load balancing, so it's not that it's a black box for us. So we have some flexibility also on load balancing through different scheduling causes. So we'll see that, and recursion is an important clause also in OpenMP. We'll see about recursion and nested parallelism. That means within a parallel loop you are again launching another level of parallelism. So these are the few points we'll look at. So if you go to OpenMP environment routines, these are the routines which have certain different functions. These routines do not give you parallelized output. If you have a code block with this routine, you cannot parallelize them. However, these routines help you to set up the parallel environment as well as to control certain features in the parallel part, also to understand how the parallel environment working on it. So, you will see some of the examples, like few we have seen the OMP set num threads. This is a function. If you call this function, the output will be the number of threads in the parallel regime. So many times, because the number of threads can be set by default or by export num threads variable which is outside the OpenMP program. So while the OpenMP program is running, many times it will be important to know actually how many threads are launched, and especially for a large program running for substantial amount of time, you really cannot scroll back and see what has been set as default. So this function can be important. Similarly, what is the number of a particular thread? You might have to run a if loop on over a particular thread, that a particular thread will do something else than the other thread. So you need to know what is the number of the thread. OMP get thread num is what it will return the ID of the particular thread. Or if we go to say OMP get num threads, it will return the total number of threads being executed in the parallel regime. So one can probably foresee the situation that it's a huge code, and at different instances, just by using OMP set num threads or by using the number of threads as a clause in the parallel directive, you are changing the number of threads at different instant, but it's a huge code, and the execution is also lengthy. So at different regime, how many threads are running, to know that it might be important for the user to know how many threads are running. So you can get OMP get num threads, which will, if you call the function, it will return the number of threads. Also, it's the number of thread is not same as the number of processors. We have seen that number of threads are many times are more than the number of processors. You have written an OpenMP job, you go to some platform, you run that OpenMP job, maybe some of the processors are occupied, some of the processors are not being allotted to your job. When you run the job, what is the number of processor that you are using? And so threads are the units of parallelism, and processors are the physically the CPUs which are crunching numbers for you. So for that, OMP get num procs will return you the number of processors. Similarly, another important environment routine is OMP in parallel. We know that OpenMP program has both parallel and sequential component. There is a master thread which is active throughout. When you come into the parallel part, it forks to multiple threads. Once the parallel part ends, the threads join, and again the master thread is active. Again, we consider the case that we are really working with a huge code, which is a large code with 10,000s of lines code, and the execution is also lengthy, it's taking days. So to see whether one particular instance is being executed in parallel mode by multiple threads or only by the master thread, it is not always possible to go into the thread program and find it out on that instant that what are the number of threads there, whether it's a parallel part or there. So this function OMP in parallel can return you that. Similarly, OMP set dynamic, if you provide a non-zero value as its clause, it will set that the number of threads will be not pre-decided by the environment set or by the default call. Rather, the number of threads will be dynamically allotted by the SMP architecture. What is architecture? How many threads are there? Based on that, OpenMP will dynamically allot the number of threads. So, even the user what has given the number of threads, but if you go to a different computer, the number of threads might be different. So, I discussed it few minutes back that OpenMP is really written for people who are using different platforms for doing their scientific computing job, and they are not many time well aware of the exact hardware they are using and what is the best way to utilize that hardware. Therefore, OpenMP compiler itself does that job, that it can look into the program and look into the hardware and set that what is the best number of threads so that the maximum benefit can be obtained, and that can be done by OMP set dynamic. OMP get dynamic will return you in true or false whether the dynamic arrangement of thread is initiated or not. What is the present environment? Are the threads statically defined by the user, or the dynamic threads are number of threads are being used? Or OMP set nested, it enables or disables nested parallelism. Nested parallelism, we will discuss nested parallelism later. It's parallel loop within a parallel loop. It's one more order of parallelization. So we'll discuss these things later. So with these environment variables, we can check which environment the parallel program is actually utilizing. Also, we can tune some of the environment parameters to get better performance, to say that is the hardware we are using, and by using this environment parameters we can get best performance. We can also do something in the code if though we are running single instruction multiple data code, but there can be some issues where some of the threads will run a different instruction. So, it will be a more towards a multiple instruction multiple data code, and that can be done by identifying those threads which will run different instruction, and that identification can also be done through the environment variables. So, these environment variables are not executables. These variables will not the instructions which will execute the program in parallel mode, but rather these are the environment variables which will help us to set the environment as well as to know about the parallel environment. So, some of the examples are first is that if we are running a program which will write that in the parallel part will write from each thread, it will write that this is the present thread ID, and to run it in multiple processors, run it in multiple threads, we have to call pragma OMP parallel. So, it will launch number of threads. While running this, if we can try to set the number of threads inside the program, we can do it as a clause of parallel, or we can write the environment variable OMP set num threads. So, the number of threads is set, and this runs over this particular number of threads, and and what is the number of identity of one particular thread, that will be obtained by the environment function call that OMP get num thread, that will return the ID which is the thread ID, and will read this. We have seen this example in last class also discussing the hello world program. So, similarly, if we need to know that we use we do not set the number of threads inside the program, we execute this program and the number of thread is set by the default or by the environment variable outside the program, and while running the program we need to know how many threads are running, and that will be done by OMP get num threads, that will give us the number of the threads. Earlier OMP get thread num was giving us thread ID of a particular thread. Here it will give us the total number of threads. So, even if this is running in parallel for all the processors, get num threads, the total number of thread is fixed, and OMP get thread num, what is the ID of this particular thread, is different for different processor. So, this will write that the total number of threads are 8, and threads 0 to 7 are running in each of these thread will write their own thread ID. So these are few environment routines example, and similarly, so we have to call the environment variables as function, or we have to take the output of the environment variable call as an integer. If you are looking for the, if you are trying to set something, this is just a function call with the integer input, which is the environment that we are going to fix. If you want to get some output of this thread, we have to call the function and associate with an output. So when we'll do a sorry yeah. So apart from the environment routines, important routines are which helps us to, I mean, which executes the parallel program, which instructs the compiler that this is a parallel part and it should be executed in multiple threads, and this is called a directive. Some important terminologies are required here to know what is directive and what are constructs. These two are very important terminology. OMP directive in C, C++, statement starting with hash pragma, or in Fortran a statement starting with a comment colon or a sentence, we will say colon dollar. It specifies the OpenMP program behavior. OpenMP directive syntax in C is hash pragma OMP, then the directive name, then the clauses can have few other clauses, and a new line starts. So this specifies that this is a part of the OpenMP program and this will be executed in parallel. Anything we started with hash pragma OMP with the directive name, and directive name, depending on the directive name, what type of what will you do in parallel mode, that will be directed. And in Fortran, this is colon dollar or sentinel OMP and directive name, and there are multiple clauses. We will look what are the clauses there. There are different types of directives. One is a declarative directives. This directive is not instructive anything. This directive is not executing anything parallel, but it is declaring that this thing, I mean something which is parallel and will have certain value for all the threads. And till today's date, the directive thread private, we have seen looked into thread private directive earlier in last class, that some variable which is private to a thread, and after the thread is destroyed and again the same thread will be launched, this variable in the private memory will remain for that particular thread. That is called thread private variable. Thread private is the only declarative directive. There can be more declarative directive which OMP may add later, but right now there is one directive which is declarative and thread private. So it starts with hash pragma OMP. Executable directive, a directive that is not declarative but placed in an executable context. So when there is an executable directive, it executes, it does something, and what it does, it parallelizes the job. It asks multiple threads to work on certain part of the program in parallel and use the concurrency. One of the example is pragma OMP parallel num threads 10. That means this parallel part will run in 10 threads and do work here. So each of the thread will do the work, whatever we asked, write a is equal to a plus 1 or something ai is equal to I, or write printf star hello world, something like that. So all the threads will do the same thing. If we ask something in parallel, whatever given will be executed by multiple threads. And the directive pragma OMP parallel num threads parallel, this part is called the directive pragma OMP parallel. This is the directive, and this part is known as clause of the directive. So we have seen that directives comes with the clause. So this is a clause that execute this parallel part in 10 threads. Standalone directive, and this we can see that this directive has an associated work with this. A part of the program is associated with this directive. In case there is no program associated with the directive, but it's still an executable directive, we call it to be a standalone directive, that only the particular statement of directive hash pragma OMP something, that is sufficient for that directive. It does not require any associated code. And pragma hash pragma OMP barrier, that means at this point all the codes should work till everybody finishes their parallel part. All the threads should work, sorry, at this point all the threads should wait, there is a barrier on the thread till all the all the threads finish their work. This is called a synchronization directive. And this is a standalone directive. So for this directive you do not need anything like this. After this directive you do not need anything like this, it will execute on its own. And loop directive, OpenMP executable directive whose associated user code is a loop in or loop nest or in form of a structured block. So here if the structured block is an iter loop, say for loop or a do loop, something like that, then we call this directive to be a loop directive. We write a directive hash pragma OMP for, and then we write a for loop. That means this for loop will be executed by multiple threads. Multiple threads will take care of different iterations of the for loop and they will execute it. That is called a loop directive. So, a few more important terminology. Construct, as we said, after the directive, especially for executable directives, there is a block of code which it executes. So, an OpenMP executive directives, and for Fortran the paired in directive if there are any, and the associated statement. So, directive, the paired in directive and the associated statement, which is either a loop or a structured block if there, not including any code which is called as routine. This is called a construct. This is the lexical extent of the executable directive. So, what this directive is doing, the next code block associated with the directive written inside the structured block of the code associated with the directive written after the directive in the till the next brace ends is called the construct. So, we can see an example that this is a program OMP, this some function is called as by OMP critical inside OMP parallel, and if you see pragma OMP parallel xy shared, this is a clause, private ix next iy next, this is also a clause. So, these are the clauses. And then after this, so this at this point we know that there some jobs will be executed in parallel and this part of the job will be executed in parallel. So, this is the entire thing is called the parallel construct. This line is the directive, and directive plus the associated code block, associated structured block of the code is called the parallel construct. That means when I am trying to execute this line, the entire construct will be executed. However, there is a function called deq, or sorry, there is no function, but if we write a function, there is a function work. So, if we call the function, what is inside the function, if we write somewhere the function work, what is inside the function, that is not part of the directive. Only these lines, that is a part of the constant, only these lines are the part of the construct. And we can see also two other directives, OMP critical x axis, OMP critical y axis. The critical directive tells that though it will be executed in parallel, at one instant only one code will execute this, one thread will execute this line, though the entire block will be executed, though this entire block will be executed by multiple threads, but at one instant only one thread will be allowed to execute this. This is called a critical directive. And these are also constructs, because this directive and the, sorry, this is not part of that. This directive and the associated line, that ix next will be executed one by the threads. This is part of the critical construct, the directive followed by its statement. Similarly, there is another critical construct. So, the executable, the hash pragma line, that is the directive, and the next part of the code which is in form of structured block or in form of a nested loop associated with the directive, that through that directive the next part of the code will be associated in parallel, whatever in the manner that the directive is suggesting. The entire thing is called a construct. And the region may also be thought of as the dynamic or runtime extent of the construct or an OpenMP library. Now, if we see here that when we call the parallel shared, we call when we call the run this construct, we call a function. Here this function, we say that it's what is inside the function is not part of the construct. The construct is only these lines, but this function is also being executed when we call the multiple threads. All the threads are also executing this function. So if we consider what is inside the function also, the entire thing is called the region, called the parallel region. So whatever the runtime extent of the construct, the function call, and what is running inside the what is the function doing, that is also everything is, or if any implicit code is there, any other implicit code or implicit functions are being called, the entire thing is called a construct, is a region, and this is called the, so this part, complete part with this works will be called the parallel region. Okay. So one of the parallel construct is in C it will look like # pragma OMP parallel. That is the parallel construct. Parallel construct means when we write this with certain clauses, whatever the part of the program in this structured block, that will be executed by multiple threads. What are the number of threads specified? Either by set num threads or by the environment variables outside the code export num threads, or by the default. When we write pragma OMP parallel, the whatever the structured block of program we write after that, that will be executed by all the threads concurrently. And in Fortran it will be $$ OMP parallel, then the block, and then we have to end the parallel block. And the clauses will be, if can be a clause, num threads. So these are the clauses: num threads, private, shared, first private, the if are the logical clauses. That means if this is true only, then this parallel part will be called. If this is not true, then this parallelization will not be done. Similarly, what are the num threads? Private, first private, shared type of variables. If there is any default, if there is any copy in, all the variables will be copied from master thread to the remaining other threads. Reduction, will look about reduction clause in detail later. So all these can be clause of the parallel. So we can say that when this parallel loop will be launched, when the parallel when the construct will be working, this will take care of this particular clauses. If some of the clauses are true, then this construct will work. If the clause specifies these are shared and these are private variable, when the construct is working, these variables will be considered like this, like that manner. So we'll see another example. So pragma OMP parallel, if n is greater than threshold, and this is a continuation life, all the clauses, so this is one clause, this is another clause, this is another clause, so all the clauses will follow the line, will be in a single line. After parallel, if n is greater than threshold, then only this parallel part will work. Then if shared nxy, then if this parallel part is working, nxy, these variables are shared variable and I is parallel variable, I is private variable. And then after that we can see there is another directive which is pragma OMP for, and then there is a for loop. So this is the construct. Inside this construct there is another directive, this entire thing is the construct. In the construct there is another directive, and this directive is associated with another set of construct. What is this directive associated with? A for loop. So when we execute this, first is this if clause. If this if clause and the shared and private, if clause is true, then only this part will be executed. And shared and private variable declaration, they are also clauses. And the OMP for will parallelize a for loop, and for loop, or if it's a OMP do in Fortran, a do loop, among the threads. That means that there are total n iterations. If we launch, say n is equal to 8, if we launch 4 threads at best, total n iterations, so total 8 iterations 0 to 7. If we launch 4 threads, 2 iterations will go to each thread, and that way the parallelization will be done, that each of the thread will take care of 2 iterations. So what is in this for loop, that will be automatically parallelized and distributed across many threads following some load balancing. We really do not need to take care of the load balancing. OpenMP is doing the load balancing for us. Only before a for loop we write pragma OMP for, it will be parallelized, and the number of threads that has been launched through the OMP parallel part, all these threads will take care of this for loop, and it will be accordingly executed concurrently. It does the load balancing too by distributing number of iterations among the thread. This pragma OMP for directive, which is for parallelizing a for loop. So for parallelizing a loop, we really do not need to do anything else, only just to call an OpenMP directive. OpenMP directive will itself take care of parallelization of the loop, and this will also take care of do the load balancing itself. There are also something called a schedule cause when calling the parallel loop, and or the for loop clause of the directive, and with this clause we can have certain control over the load balancing. But otherwise, if we do not call anything, by default it will also do some load balancing, and which is not bad. This load balancing is most of the time quite useful, and distribute the iterations among different processors. It will be parallelized in that way. The directive can be written within this directive, pragma OMP for this directive can be written within a parallel block only. This is what is pragma OMP for. You have a for loop, and pragma OMP for has parallelized it, has distributed the for loop into multiple threads. When can it be done? When multiple threads are there. To launch multiple threads, you need a parallel construct. So you need a parallel directive. So this pragma OMP for should be a part of the parallel construct only. Well, this directive is not applicable if the iterations are independent. This directive is applicable only if the iterations are independent. In case the iterations are dependent, that xi is dependent on xi minus 1, we cannot parallelize it. There is no concurrency. If xi requires xi minus 1, then xi and xi minus 1 cannot be calculated concurrently. So there is no concurrency, and we cannot parallelize it. And we can see an example. So only if these iterations are concurrent, each of these iterations are independent and they can be run concurrently, then pragma OMP for is meaningful. We can see an example. So what we are doing here, that OMP set num threads is equal to 3, pragma OMP parallel private I ID are private, A is shared, and there is a loop I is equal to 0 to 9. For that, ID is OMP get num thread, and AI, there is a variable A whose each of the element is the ith number plus 1. So A0 is 1, A2, A1 is 2, so on, and it will write that the value of A is this, A1 is this from the thread number. So what will it do here, that multiple threads will be there, and this particular, what is the construct here, if we see, one is what is called inside the pragma OMP, what is called inside pragma OMP parallel. This is executed by multiple threads. This is a construct, and then we call pragma OMP for, and what is called within pragma OMP for, this is another construct. So this is always, this OMP for is always part of another construct, of our parallel construct, and this here I and ID is private, is shared. These are the clauses. Now there is a for loop. For I is equal to 0 to 9, AI is I plus 1, and printf the values of I, and this for loop is parallelized by pragma OMP for in the number of threads. The number of threads is set by set num threads is set to be 3. This will run on 3 threads. Okay. So if we see the output, let us erase this, that A0 is 1. So 3 threads means total 10 iterations. We have not done any load balancing, but OpenMP has balanced the load some way that 0th thread gets 4 iterations, first thread gets 3 iterations, the last thread gets 3 iterations. So it's the best load balancing possible. Well, and we write that for first 4 are done by 0th thread, then they are done by first thread, and then this is done by second thread. And this is possible because this calculation is independent for any iteration, all the iterations are independent. We do not need to know value of A2 to calculate A3, or we do not need to know value of A0 to calculate A7. All of them can be calculated independently. If the iterations are dependent, then what happens? Then we have written AI is AI minus 1 plus AI minus 1 plus 1, and this is written in the same place, that this part is replaced by this. We have the same code, only the for loop is replaced by this part. And what will happen if we execute it? That we understand that AI minus 1, so when the first thread is operating, A0 AI minus 1 is undefined, so it will probably pick up 0 because the stack will help, though it's outside the range, outside the memory bound, the stack will help. For the second thread, which starts from, or thread 1 which starts from I is equal to 4, A3 is not known because A3 has gone to first thread. Though A is a shared variable, first thread has not calculated A3 by that time. So what is the initial value of A3? It is by default initialized by 0, it will pick up 0. So the second thread will start calculating from 0. It might not pick up anything if the values are, as the values are not available, as A3 is not calculated. So what happens? The execution is quite interesting. The first thread picks up everything, initial value 0, and then keeps on adding 1 with that, because it was it somehow thought that it is initialized with 0, though the initializations were not done. The first thread was also done, initialization was by default 0, so it starts with again picks up 1. A4 is the first iteration of thread 1, it picks up A's value 0 and adds 1. This is also first iteration of 1, it picks up 0 and add 1, and then for the next one it keeps on, next values of A it keeps on adding 1. But this is a shared memory variable which is being accessed by multiple variables, and this is not rightly updated. This is a invalid for loop. So the last thread actually picks up garbage values, so these are locally updated by each of the do loop, but the last thread is working on garbage values because these values are not rightly updated. The last threads are picking up garbage values. Well, so one has to be careful to see that the threads are independent, the iterations are independent in order to parallelize it. If the iterations are dependent, you cannot parallelize it like this. And with this we come to discuss about the different work sharing directives, because we have seen that if there is a parallel loop, it will be shared by across many threads by parallelization, by the right directives. So one is pragma OMP for, or in Fortran this is $OMP2. This will do a distribution of the loop. If there is a iterative loop after this, the iterations will be distributed among the threads. But many times the jobs are not like distribution of not like an iteration, not like a do loop or for loop. Many times it will be seen that there are different parts of the jobs which can be run concurrently. Think of a task dependency graph, that we can find out these are the concurrent jobs which can run, but they are not parts of iteration, they are something else, but they can be run concurrently. We can use pragma OMP sections and define different sections, and each section will take care of each part of the job. And then we can use pragma OMP if there is another work sharing directive, if only one thread has to take care of that part. It's inside a parallel regime, because these are called within the parallel region. Inside the parallel region, we understand that for cannot be called outside the parallel construct. It's part of a pragma MP4 is part of a parallel region, and when we are doing work sharing, already the threads are activated. Within that, if some certain portion is required to be executed only by one thread, we can use pragma MP single. Then one of the threads will be asked to execute that. There are some similar things. Pragma MP master, only master thread, that is thread ID 0 will execute that code block, and pragma MP critical, we have seen that it's indeed within a parallel region, one particular part is actually not parallelized. That means one by one threads we are executing this part, and this is usually done to avoid contention and false sharing, shared data accessing issues, that one thread will do something, next the other thread will come and work on that same variable like that. So this is done by pragma MP critical, and these are the work sharing directives in OpenMP. We will look into the work sharing in OpenMP in more detail in next class. Thanks.